and welcome to this manufacturing systems technology part 2 module 30. We were discussing about the various joint configurations and how you represent them in terms of notations, and in line with this we had done several joint notations earlier, where we were talking about to start from the body side of the robot. Like in this particular case, for example, we discussed that in order to notate this particular robot joint, you start from the body of the robot and proceed to the lower arm, then the upper arm, followed by the wrist, followed by the end effector, and you have to mention about what kind of joint the concerned arm would be in unison to represent this the robotic joint fully. So, in this particular case, for example, we started with a linear lower arm, we started with a linear upper arm, and then we started with a twisting wrist. The wrist is capable of twisting and rotating. Rotation of the wrist is basically in this particular case is in this particular direction, and the twisting is in this particular direction, and so is the end effector's twist. So, you have the end effector also capable of twisting. So, you have a twisting, rotating, twisting kind of configuration. So, in fact, we represented this joint notation as linear lower arm, linear upper arm, and twisting wrist, rotating wrist, and twisting end effector kind of configuration. In a similar manner, this can be represented as a rotating lower arm, rotating upper arm, and rotating upper second arm, and then you have obviously the TRT, that is the twisting, rotating, and twisting configuration as far as the end effector and the wrist goes. In this particular case, you would have TL, TRT, that is twisting configuration of the lower arm, a linear configuration of the upper arm, and then obviously the TRT means the twisting wrist, rotating wrist, and the twisting end effector. So, this is how you represent most of these robot joints. Some more examples: this can be represented as LRL, TRT, and in fact, I would go ahead and request all of you to sort of figure out how this notation arrives at from this particular joint. Then again, you have RRL, TRT, you have TRL, TRT, and finally LVL, TRT. As you know, the V stands for the revolving kind of an orientation. So, that is how you represent the following robotic joints. So, having said that, now we would like to go to the classifications and the reach of the various robots. So, normally the robots are classified on the basis of their physical configurations, and they are also classified on the basis of the control systems which are adopted. So, there are 4 basic configurations which are identified with most commercially available industrial robots. One is the Cartesian configuration, another is the cylindrical configuration, then the polar configuration, and the jointed arm configuration. So, the Cartesian configuration is shown here in figure A, and it consists of links connected by linear joints. For example, in this case you can see there is one linear joint in the x direction, one in the y direction, one in the z direction, and this configuration of the robot is typically joint notified as LLL. Okay, and these are like gantry robots. For example, you can see this is one of the gantry robots which may be used for doing laser micro machining, for example, where the laser head can be mounted here and the workpiece can be mounted on the base, so that you can have even lasers writing on vertical faces as well as horizontal faces of different systems. Again, you have cylindrical configuration, whereas the name suggests, is shown in B, basically there is one rotation axis, like there is a theta axis over which the arm can rotate, and the y and the z motions are again linear in nature. Okay. So, you have one rotary joint, and the base and the linear L joints succeed to connect the links. The robot arm in this configuration can be represented as twisting linear configuration, and the space in which the robot operates is a cylinder. We have similarly polar configuration, as the name suggests, shown in C again, where you have a workspace of spherical shape. So, if you have a probability of moving the lower arm around this axis. So, twisting the lower arm at an angle theta and rotating the upper arm around this particular axis at an angle beta. So, obviously you are covering, and then you have also a linear actuator at the end which can be able to make the reach of the robot from one particular radii to another. So, this actually corresponds to a spherical shape, creation of a spherical shape in space, and this joint can be notified as either TRL or TRR depending on what is the end effector like. So, that is how you have polar configurations. Obviously, you also have jointed arm configurations as shown in D, which is a combination of cylindrical and articulated configuration as illustrated here. The arm of the robot is connected to the base with a twisted joint, as you can see here, right about in this particular portion. So, you have this mechanism which twists about the angle theta, okay, about the vertical axis. The links in the arm are connected by the rotary joints, as can be seen. One rotor, one joint moves at an angle beta, another at an angle alpha, and the rotations generally take place in the vertical plane. So, that is basically a combination of cylindrical and articulated configurations together. So, these are how robots are generally classified. So, you can see the various configurations of the robot and their reach drawn here, for example, by these dotted figures. This is a cylindrical robot in case B, and the reach that this robot has is given by this dotted envelope around which the end effector can basically move given the base location of the particular robot. Similarly, you have a Cartesian robot as in C and a polar coordinate robot as in A, describing the spherical zone over which the robot can go, or in this particular case the Cartesian system over which the robot can basically go and spread. So, that is how you represent different robotic configurations. So, we now classify the robots based on control systems. So, based on control systems adopted, robots are classified into point to point robot, controlled robot, continuous path controlled robot, and controlled path robot. So, let us look at what these various classifications are. So, the point to point robot is capable of moving from one point to another point. The locations are recorded in the control memory. PTP robots do not control the path to get from one point to the next point. The programmer exercises control over the desired path to be followed by the programming a series of points along the path, and common applications of these include insertion, spot welding, hole drilling, machine loading, unloading, crude assembly operations, etc. The continuous path control robot, on the other hand, is capable of performing movements along control paths. So, with the continuous path control, the robot can stop at any specified point along the control path. Basically, it is a continuous operation. So, the simplest example is a straight line. For example, if you have a robot moving equal to, so in a straight line, for example, if we take the robot and lead it to go along a straight line and record the control points in between in the memory, obviously dependent on the resolution, stage resolution, and other factors. Whenever you execute the motion, the complete motion to go on a straight line, the robot will just follow those control points which have been recorded in the process of training it by taking it along physically on the path of the straight line. So, the only difference between the point to point and this case is that in a point to point control, you can, once given the location of the destination, the robot cannot be stopped in between. So, it starts from a certain point, ends at a certain point. In between points, there are no ways of stopping or not executing the particular trajectory, and that is a big problem in the point to point. But in the continuous path control, now because you have already had a training phase where the whole path has been planned into discretized coordinates, and those coordinate locations have been stored in the robot control memory, it is easy for the continuous path control process to stop the robot at any given path. Some of the continuous paths can also be curved paths. Okay, so, the curved paths can also be typically defined. The programmer manually moves the robot arm, even it is a curve or it is a straight line or any other particular motion, and the controller unit is supposed to store the large number of individual point locations along the path in the memory. That is how the robot learns. There are other higher level robots which work on controlled path mechanisms, and so the only difference in the controlled path is that the control equipment can generate paths of definite geometry such as straight lines, circles, interpolated curves. So, there is a relationship which is available algebraically, in which there is some computational first hand activity carried out by the robot controller itself, and so The question there is good accuracy by means of looking at the resolutions of the various stages, looking at the controller resolution to map the data, so on and so forth, and that defines what is the resolution of the least count of motion on a certain guided path or a controlled path as given by a relationship. Okay. So for example, y equal to mx plus c is a straight line equation. So if a robot is supposed to go on a straight line, automatically computationally the predicted y versus x coordinates would be generated, okay, which will give you a set of control points for the robot to automatically self guide on that particular path. So robot reach, it is also known as a work envelope or work volume, in is the space of all points in the surrounding space that can be reached by the robot arm. I think we had already shown you the envelope, the dotted envelope around a spherical coordinate robot, spherical accessible robot or a cylindrically accessible robot, etc. And it really depends on two things. One is the mounting point or the end location at which the base of the robot is fixed, and what is the reach of the end effector given the maximum flexibility executed in that system and the maximum stretch executed in a particular system. So that is how you will define the robot reach. So reach is definitely by and large one of the most important characteristics to be considered in selecting a suitable robot, because the application space should not fall outside the selected robot's reach. So that way the robot motion cannot execute the job properly if the application's point is outside its domain. So for a Cartesian configuration, the reach is a rectangular space, cylindrical configuration it is a hollow cylinder, polar configuration is a part of the hollow spherical shape, all you have seen before by the dotted lines mentioned earlier. So the other important aspect in robotics is obviously about the kinematic transformations. They are robots are, as we already know, are systems with various linear revolving rotating twisting kind of links, and there are different length aspects and angular aspects which are associated. So obviously there is a geometrical relationship between the base of a robot and the end effector and the way it moves with respect to the base. So in robot motion analysis, obviously we study this geometry of robot arm with respect to the reference coordinate system, which is typically taken as the base of the robot in most of the cases, while the end effector moves along the periodic path. So the kinematic analysis involves two different kind of problems. One is obviously to determine the coordinates of the end effector for a given set of joint coordinates and angular relationships, and the vice versa, which is determining the joint coordinates for a given location of the end effector and the end of the arm. So it is basically in one case a forward kinematic transformation starting from the base of the robot towards the end effector, and another is the backward kinematic transformation. So the position V of the end effector can be defined in Cartesian coordinate as xy, and generally for robots the location of the end effector can be defined in two systems. One is the joint space and the world space, also known as the global space. So in the joint space, the joint parameters such as rotating or twisting joint angles and variable link lengths are used to represent the position of the end effector. So obviously for a rotating kind of system, you have two different rotation coordinates, one is let us say theta, another is alpha. So the position of the end effector in the joint space is recorded in terms of a theta and an alpha angle. Similar case is in the case of a linear robot system where you have two different link lengths, let us say L1 and L2. So these are mostly used for defining the position of the end effector. If it is a twisting linear kind of a system, you have a twisting angle and length which is associated to derive the Vj or the position coordinate of the end effector. So in a world space, rectilinear coordinates with reference to the basic Cartesian system are used to define the position of the end effector. Usually the origin of the Cartesian axis is located at the robot's base, as I referred before, and Vw refers to the position of the end effector in the world space. So obviously if the origin is shifted, then the base of the robot, then there is a problem. Otherwise whatever is the readout of the end effector in the joint space is usually considered to be that in the world space as well. So let us look at the various systems which are into place. This is for example a linear system. So you have this, for example, is a LL robot, linear robot, which means here that this right here is the base of the robot. Let us just classify first the different aspects related to of the robot. This is actually the, you can say, the lower arm, and it is pretty immovable. So, basically there is no possibility of linear motion along this particular arm. The only two linear motions in this particular case, one is a linear along L2, another is a linear motion along L3. So, you have a linear system here, where the upper arm is able to move, and so is the end effector, or the wrist, you can say, is capable of movement. Okay. This is the wrist. So, having said that, obviously if you were to change everything in terms of the world coordinate system, here is the origin of the world coordinate system. In this particular case, it is a very generic case. You can see the base is not really aligned on the world coordinate system, and there is a readout of a joint J1 here, which is x1 y1 in this particular space. So, this right here is x1 and this right here is y1. Okay. So, that is how the readout is. So, obviously with respect to this x1 y1, we will probably have to find out, use some kind of a homogeneous transformation, where we can actually plot what is the x and y. So, we will use the following transformation equation for that, x equal to TLL x1. I am not really going into the details of how mathematically these can be established, because this I have done in a very detailed manner while doing the computer aided design. So, in a similar manner, let us say in this case the matrix which comprises of the end effector position, that is x and y coordinate, can be represented as x y 1. It is of course a 2D space that we are working in. So, the transformation matrix for establishing the linear movements can be represented as 1 0 L2, which is the length of this particular link, and similarly 0 1 minus L3. Again, L3 is in the reverse direction. So, it is in the minus y direction. You have to be very careful about establishing this, and then you have 0 0 1 as the dummy coordinate. And so, the other aspect here, x1 is obviously the coordinate system in the world space, that is x1 y1 1, which is being read out very well with respect to the origin of the world space. So, if we know where this particular joint J1 is located, and in fact this joint has a relationship with the base. So, we can actually further allow this particular base here to be represented as x1 and y1 minus L1. Okay. So, that is how you can actually see with respect to the base as well, but the forward kinematic transformation here means x becomes equal to x1 plus L2, and y becomes equal to y1 minus L3, and that is how you can actually read out the point x y with respect to x1 y1. Okay. So, everything is converted now into the joint space from the world coordinate systems x1 y1. If supposing we knew the location of the, or we wanted to know the location of the base in this particular case, the obvious answer to this would be that the base is located at x equal to x1, which is actually x minus L2, and it is located corresponding to y1 minus L1, which is actually y plus L3 minus L1. Okay. So, that is how you can locate the base once this end effector position is determined with respect to the world system. So, that is how you do the forward kinematic transformation. You can actually go back and do the reverse order of it. So, you can say that if I knew x and y, so if we knew the position of the end effector, can I derive from the end effector position the world space coordinate. So, in this particular case, as you know, x1 is equal to the end effector position minus L2, and the y1 is equal to y plus L3, the end effector position y coordinate plus L3. So, these are the reverse transformations. So, these are the reverse kinematic transformations. So, this is the forward, that means from the world coordinate system to the end effector position, and the reverse kinematic is, if we know what is the end effector position, can we map back what is the world coordinate system or what is the joint space based on that. So, this is how you map the kinematic transformations. A similar example can come in case of rotation kind of systems. Here you have two links, as you can see, lower link being fixed. So, this is the base of the robot really, and you have a lower arm and an upper arm as given here. So, let us call it LL and UL. Okay. And here you already know that there is a movement of rotation along the joint J1 in the two dimensional space, which is rotating at an angle of theta along the J1 point, and then let us say the link L3 is rotating with respect to the L2, but then with respect to the world coordinate system, that is with respect to the horizontal or x axis, it is rotating at an angle alpha. Okay. So, having said that, now there would be an existing transformation, and we can write this equation as x equal to the transformation matrix of this double rotation TRR times of x1, where x becomes the end effector space, which is x, y and 1, coordinate x, y, 1, and the TRR in this particular case becomes equal to 1 0 L2 cos of theta plus L3 cos of alpha minus theta and 0 1 L2 sine of theta minus L3 sine of alpha minus theta, where alpha is basically the total motion which has been moved with respect to I am sorry, this total motion with respect to of the L3 with respect to L2 as described by alpha, as I had verbally illustrated before. So, this angle really becomes equal to alpha minus theta, because theta is this angle which is describing the motion of L2 with respect to the horizontal, and the total angle that it has moved with respect to the initial link L2 is basically alpha. So, this right here is really alpha minus theta. Okay. So, that is how you have represented this, and then you have 0 0 1 and this right here is the x1 coordinate, which is related to what is the world space for the joint J1 x1 y1 1. What it essentially means is that we are looking at coordinate x here, which is right about this point, which is actually equal to x1, the coordinate here, plus we add the component of L2, which would contribute to displacement of the point x from x1, which is L2 cos of theta. So, L2 cos theta is really this much movement because of the angular twist of the link L2 with respect to the horizontal, and then the other part here really is about the link L3, and you have a cosine component alpha minus theta. So, plus L3, which is this link right here. So, the cos of alpha minus theta, which is actually same as this alpha minus theta relative motion of link L3 with respect to the world coordinate system, which comes into picture. So, L3 cos of alpha minus theta. Okay. So, that is how x is described. Y again, the end effector position is described in terms of y1 plus L2 sine of theta. So, obviously, there is going to be a addition between this y1 and y2 as given here. So, a part of it would come as a contribution from L2 sine theta. So, this link right here is at least L2 sine theta displaced from y1 in the vertical direction, and then you have minus of again L3 times sine of alpha minus theta, which is actually the negative contribution because this link has now moved below the horizontal. So, that is how you describe the y. So, obviously, if I were to do this is the forward kinematic transformation. So, we can actually write down the reverse kinematic transformation in this particular case by just changing given the end effector position, how will you calculate the different joint coordinates, like what is the link L length of the link L2 or L3, you can find out from the reverse transformation. That we will do a little bit later. So, that is how you do the rotation robot. We also have another case here, the twisting linear robot. Here the robot is twisting along the joint J1. So, there is an angular movement alpha along this twisting. So, it is capable of actually going in this xy plane in both the directions, and then there is a linear movement L2 of J2 with respect to the end effector position xy. So, that is why we call it a TL robot. And here also, if I look at the transformation equations, the x would be actually the transformation for the TL configuration and times of x2, where this x2 y2 here is obviously the location coordinate of the joint J2. Okay, so, the base here in this case is the joint J1, which is the first joint which is performing this twisting rotation. So, here I can write the transformation as xy1 equal to the transformation matrix, which is in this case 1 0 L2 cos of alpha, 0 1 L2 sin of alpha, 0 0 1 times of x2 y2 1. And obviously, if I knew the link length here as L1, I would say that I have a relationship that y2 is equal to y1 plus L and x2 is same as x1. So, that is how I would be able to convert or get the location of the joint J1 once this world coordinate system has been defined. So, these x2 y2 or x1 y2 are defined in this whole world coordinate system, and the end effector position is actually what we are trying to determine in this particular case through this transformation. So, that is how you do the forward kinematic transformation. So, obviously, if you were to look at, can we do the reverse. So, that is how the forward kinematic transformation of all the three systems, that is the linear, the rotary and the twisted linear kind of robot arms have been defined. So, in a nutshell, if you look at the forward kinematic transformations here, this slide mentions about the combined, how the transformations, the forward direction would happen. So, if x1 and y1 are in the global coordinates as the position vectors of joint J1, the first joint. So, obviously, the end effector xy would be related as the vector x is the transformation matrix T linear x1. Similarly, for the RR robot, the rotational robot, you have a coordinate transformation given by x equal to TRR x1, where TRR again is this particular matrix right here as we derived in the last step, and similarly for the TL robot. The similar kind of a transformation can happen in the backward direction if you know the end effector position vectors and also the initial position of the joint J1. So, you can obviously be able to find out what are the link lengths. So, these are in the joint space, so you are basically transforming from the global coordinate system into the joint coordinate system. So, L2 and L3 can be calculated as x minus x1 and y1 minus y. Similarly, if you wanted to look at the joint space, what are the angles of movement? So, cos alpha and tan alpha are divided by either the link lengths and the global coordinates of the end effector as well as the base of the robot as x minus x1 square plus y minus y1 square minus L2 square minus L3 square by twice L2 L3 equals cos of alpha, where alpha again is this particular angle of motion. As you know, this is the overall angle of the motion, and this is the angle of the link L2 with respect to horizontal angle theta. So, therefore, this becomes alpha minus theta. Okay. And tan of theta here can be defined as y minus y1 times of L2 plus L3 cos alpha plus x minus x1 times of L3 sin alpha divided by x minus x1 times of L2 plus L3 cos alpha minus y y1 L3 sin alpha. So, I leave it on to the audience to sort of figure out how these reverse transformations have happened given the forward transformation. This has been detailed in manufacturing systems technology part 1 and the CAD module. Similarly, if you wanted to find out the joint link length J2 between the L2 between the joint J2 and the end effector can be looked at by looking at x minus x2 square plus y minus y2 square whole under the root, and similarly the twist angle sin alpha can be determined as y minus y2 divided by L as the amount of angle that has been moved in a axis vertical parallel to the z axis in this particular case. So, these are the backward kinematic transformations. Let us do some problem examples. Let us say an LL robot, linear robot has two links of variable lengths. Assuming the global coordinate system is defined at joint J1, determine the following coordinates of the end effector points. Link lengths are given to be 3 meters and 5 meters. So, obviously, if I were to look at this particular robotic system, saying that the global coordinate systems is defined at the joint J1. So, therefore, the joint J1 is defined at the point origin. Okay. So, this probably is the definition of this kind of robot, and the J1 joint signifies the base of the robot, and the other end effector is at again a variable length. This is the end effector. Okay. So, when we are talking about 0 0 as the global coordinates for the joint J1, the coordinate of the end effector point if variable link lengths are 3 meters and 5 meters, meaning thereby that you have 3 meters and 5 meters as the length L1 and L2. So, therefore, the coordinates of the end effector should be 3 5. Okay. And the variable link lengths if the end effector is located at 3 5 also should be 3 meters and 5 meters. So, very simple forward and backward transformation. This is the forward transformation, this is the backward transformation based on the logic that has been given earlier. Similarly, if a RR robot, a rotation robot has two links of lengths 1 meter, assuming the global system is defined at joint J1. So, in this particular case, let us say you have a RR robot defined in this particular manner. So, the first link, which is at 1 meter in length, is basically or positioned about the origin. So, that the joint J1 comes at the origin exactly 0 0 of the global coordinate system, and the other link. So, this link has gone about 30 degrees, and the other link also rotates in the other direction about 30 degrees, which meaning thereby that the link comes back to the normal position. So, this rotates again by 30 degrees, meaning thereby that this link is at 0 angle with respect to the horizontal, and this is about another 1 meter. So, obviously, we need to find out what is the end effector's position coordinate right about here, which I can just apply the matrix and find out, or even geometrically it can be found to be 1 plus the cosine component of 30 degrees or of 1 meter, which is 0.8667. So, essentially this should be 1.8667, and the y component here should be the sine component of 1, which is about 0.5 meters. So, that is how we will define the end effector's position in this particular case. Also, by the transformation matrix, the TRR in this particular case would be represented as 1 0 1 cos of 30 plus again 1 cos of 0, okay, 0 degrees, and because this is alpha minus theta, which is actually equal to 0 now, 30 minus 30, and then the second line becomes 0 1 and L2 sin theta, that means 1 sine of 30 degrees minus 1 cosine of 0 degrees, okay, and then you have 0 0 1, okay, as the transformation matrix TRR. So, this actually becomes equal to again 1 0 1.8667 and 0 1.5 0 0 1, and this actually is multiplied to 0 0 0 0 1 in order to find out the new coordinate system. So, the position vector for the end effector x y 1 should be equal to this TRR 1 matrix 1 0 1.866 0 1.5 0 0 1 times of the matrix 0 0 1, which is the coordinate vector of the joint J1 in this particular case, and so this x y would actually become equal to 1.667 and y would become equal to 0.5 as illustrated here. So, even using the transformation as well, you see we are able to figure out or map the end effector's position given the joint J1's position at the origin. So, a similar case of TL robot, and this I leave to your judgment, how would you work on it. So, you will have to assume the coordinate system is defined at J2. Okay. So, meaning thereby that the joint J2 in this particular case happens to be the coordinate system. This is the joint J2. Okay. So, it is capable of twisting around these axes and also capable of moving linearly. So, that is why it is a TL robot, and you will have to find out the coordinates of the end effector if the joint J1 twists by an angle of 30 degrees. So, basically this twist here of the joint is by a certain angle. So, it goes here in the xy plane. This is the xy plane, let us say this is the z axis, right, and so this twists by 30 degrees and it is able to, the total length of the variable length of the arm is about 1 meter. So, you will have to find out what is the end effector's position coordinate. So, obviously it will be the cosine of 1 and cosine of 30 degrees and sine of 30 degrees times 1, and you can actually figure out, do the variable do the backward transformation to figure out that if the end effector position is defined, you can actually see what is the angle of twist or even the link length, etc. So, that is how you can actually attempt these problems by looking at the transformation matrices. A little complexity is added by putting a third dimension. So, here for example, you want to translate the end effector position of a robot in 2-dimensional space. So, obviously this is a sort of translation matrix that you are looking at, particularly in a linear system. But when the space is a 3D space, then obviously you will have to add a dummy variable, and this I had illustrated clearly in the coordinate transformation module that we had done in the manufacturing systems technology part 1. So, you basically homogenize the matrix by adding or taking the matrix from a n space to n dimensional space to n plus 1 dimensional space, and then that becomes very easy to again multiply and find out the modified coordinate system. So, here in this case we just add a dummy variable 1 to the 3-dimensional coordinate system that is there, RST. These are the initial vectors and this is the transformation matrix. So, the transformation matrix into the initial vector becomes the final end effector position. In this particular case, for example, they are talking about distances 5, 10 and 15 respectively translated in the x, y and z directions by the end effector. So, we will have to write the transformation matrix if the initial point position of the end effector is 2, 1, 2. So, therefore, the transformation matrix can be written down as 2, 1, 2, 1 times of the whole vector space here 1, 0, 0, 5 distance of movement, 0, 1, 0, 10, 0, 0, 1, 15 and the dummy variable 0, 0, 0, 1. Okay, so, that becomes the location of the end effector. So, let us lay this out as x, y, z and 1, and so obviously as you can see in this particular case, the transformation x, y, z 1 would result in 7, 11 and 17 respectively. So, that is what would be the modified end effector's position in this particular case. So, you can do a similar kind of a transformation with a rotational coordinate system. So, let us say a point vector is rotated about x axis by an angle 90 degrees. So, you will have to write the transformation matrix in this particular case. The initial position of the end effector before rotation is given to be 5, 2 and 4. So, you want to determine the new position of this point. So, obviously the rotation vector, if it is about the x axis, is given by the transformation here 1, 0, 0, 0, 0 cos alpha minus sin alpha 0, 0 sin alpha cos alpha 0, 0, 0, 0, 1, and alpha is rotated about the x axis in this particular case as has been given by 90 degrees. So, we would like to apply this transformation to the modified or homogenized vector. So, initial position of the end effector before rotation was 5, 2, 4. So, we multiply the transformation matrix here, which is 1 0 0 0 0 cos of 90, which is 0 minus 1 sine of 90, 0 0 1 0 0 and 0 0 0 1. So, that becomes the final point of the end effector after the rotation has been executed here. This is cos of alpha, cos of 90 degrees, or sine of 90 degrees, and again sine of 90 degrees and cos of 90 degrees. So, if you look at how the rotational space has been, or matrix transformation matrix has been given about the x axis rotation, it is represented here. I am not going into the detail of how to prove these, because they have been extensively done in the CAD part of the course, which was manufacturing systems technology part 1. So, obviously now we can write this modified coordinates as 5 minus 4 2 and 1. So, that is how you do the modified coordinate of the end effector, particularly in this kind of situation. So, you will have to be very careful about applying these translating vectors. So, about y axis and z axis, the translating vectors or the transformation matrix changes as cos beta 0 sin beta 0, beta is the rotation about y axis, 0 1 0 0 minus sin beta 0 cos beta 0 0 0 0 1, so on and so forth. And about the z axis again, if gamma is the rotation, then you can actually have the transformation matrix written as cos gamma minus sin gamma 0 0 sin gamma cos gamma 0 0 0 0 1 0 and 0 0 0 1, so on and so forth. So, that is how you basically modify the coordinates. I think we have covered more or less everything that needed understanding in the robotics area. So, the other most important issue is about the robot selection. And then also the applications of robots to various industrial processes and systems. So, obviously because the robotic applications in the industry has sort of grown heavily, and there has been an exponential growth in the variety of automated techniques and operations. The applications obviously of the robots have increased to a vast numbers, and the technical features which are involved in planning and suiting the requirements to a certain robot also has outnumbered quite a bit. So, what are the prime considerations in selection of a robot? Let us just briefly look at one or two of these very main guidelines which would be used for doing selection of robotic systems to certain processes. So, the most important features that we need to look at when we select a particular robot for a certain situation are obviously number 1, degrees of freedom. Okay. What all is needed in terms of its motion sequence, control system that has to be adapted, the work volume that it has to cater to. Typically all robotic applications are for repetitive kind of assembly line kind of work, load carrying capacity, accuracy, repeatability, so on and so forth. So, the characteristics of a robot generally considered in a selection process include the size of class, the size of the robot is given by the maximum dimension x of the robot work envelope. So, there are different classes, there are at least 4 different classes based on the different ranges of x which can be accomplished. These are the micro, which typically goes for less than 1 meter range, less than or equal to 1 meter range of the working envelope. Small range, which is actually between 1 and 2 meters, medium between 2 and 5 meters, and then again large ranges for at least more than 5 meters or so. The other issue is the degrees of freedom. So, the degrees of freedom can be 1, 2, 3 and so on. So, the cost of the robot obviously increases with number of degrees of freedom, additional number of degrees of freedom. There can be velocity considerations also, which are affected by the robot's arm structure. So, there are various types of arm structures. For example, the arm structures can be rectangular, cylindrical, spherical, articulated arm, horizontal. All of these you have more or less seen earlier. The selection process can also be on the basis of actuator types. There are various types of actuators: hydraulic, electric, pneumatic. Each of them has its own pros and cons. I think we have illustrated quite a bit of it towards the beginning of this lecture. And then obviously the control modes, which are very important. They can be either a servo point to point, or a continuous path, or a combined point to point continuous path, or a non-servo mode of control. So these are mainly the so called most important criteria which have to be used looking at a certain application to fit a certain robot with certain specification to that particular application. So I would just like to now look at some of the typical applications which are becoming an integral part of the automated manufacturing system. So the common industrial applications of robots in manufacturing involve typically loading and unloading of parts, and they can include various domains like robot unloading parts from die casting machines, or robot loading a raw hot billet into a die, holding it during the forging and unloading it from the forging die, robot loading sheet blanks into automatic presses with the parts falling out of the back of the machine automatically after the press operation is performed, robot unloading molded parts formed in injection molding machines, or robot loading raw blanks into NC machine tools and unloading the finished parts out of the machines, so on and so forth. So basically the concept when the robotics really emerged was that it would be typically subjected to those environments where there would be a personal safety hazard involved with deployment of manpower, and so that was the initiation of where robots would really start to occupy. Now it has expanded to a variety of domains. In fact, wherever there is a flexible automation, it has probably become an integral part and a necessary part of manufacturing processes for industrial automation to be complete. Let us just look at some representative pictures of some different robots. This right here shows a welding robot in a car industry. There is a weld shop. So this is basically probably a line which is it's a final line in which the car body is already more or less assembled, and the roof needs assembly, and the remaining parts like the front fenders, left and right, the main floor, the side bodies, etc., and all the framework has already been put in place. So you can see a variety of robots here which are doing welding operations. Most of them are spot welding operations on this car line. Another application here is basically a robot with special engineered tooling. So basically inserts 4 valves into an engine cylinder head, obviously matter of precision again. So every time there is a engine cylinder in place, the valves are being inserted into the head of this engine cylinder before assembling it to the final block, and there is a matter of precision. So again a very good application of robotics. This right here is a robot mounted on a riser, IRB 6000, palletizes different size box. So it picks and places basically the boxes from this location into the location desirable. Probably it is some kind of a conveyorized system which is supplying to another end user who can be an assembly line, or which can be again a weld line. So these components need to be destacked and supplied, for which again repetitive operations and robotics is deployed. Again a deburring robot, IRB 3000, which is deburring transmission housing, very important for again assembling gearboxes onto the engines. So this is another fundamental robotic application for industries. This is one where IRB 2000, it shows sealant application in headlamps, particularly the headlamps need to be rainproof, and so there is more or less a requirement of putting sealant on the inner and outer covers, between the inner and outer covers of the headlamps. Here the same is being done on a robotics line. It's in fact a top view that is being shown here. This right here is probably the sealant application robot doing its job. So that's about more or less everything that we had on robotics applications. The other important offshoot of this automated industrial applications happens to be automated material handling and storage systems, and here there is a lot of research which is ongoing in most of the industries with the viewpoint of saving inventory costs, inventory carrying costs, and trying to minimize to the level of the sort of lean manufacturing, which we have taught in details in the earlier lectures in manufacturing systems technology part 1. So what is a material handling system? Part of industrial automation. So it is a system that can simply be defined as a integrated system involving such activities as handling, storing and controlling of the materials. And obviously the word material has very broad meaning. It can cover all kind of raw materials, it can cover work in progress during an assembly for example, or during a subassembly for example. So you have subassemblies and finished assemblies all involved as materials, and the flow of which is needed at some point of time in the whole production process. The primary objective of using a material handling system is to ensure that the material in the right amount is safely delivered to the desired destination at the right time, and that too at a minimum cost. And so therefore this question of automated material handling and storage systems arise. So let us start with some of the basic principles of material handling as figured out by the Material Handling Institute. It has basically compiled about 20 basic guidelines, some of which I will be sharing below, for the designing and operating material handling systems in place. So the first principle is orientation principle. It means study the system relationships thoroughly prior to preliminary planning in order to identify existing methods and problems, physical and economic constraints, and to establish future requirements and goals for an organization. And that is in fact the first element of study to begin with just before planning any material handling system. So then there is a planning principle which establishes a plan to include basic requirements, undesirable options, and consideration of contingencies for all material handling and storage activities. Things like what is the distance of the vending source from the consumption source, etc., and how much is the level of inventory that has to be maintained is planned at this particular planning level. Then there is a systems principle. So basically look everything as a systems approach. So you have to integrate the handling and storage activities that are economically viable into a coordinated system, also known as Yoidan. If you remember in the lean manufacturing there was something called Yoidan, at least in the subassembly level, where there would be a coordinated movement of the various units so that they could be finally assembled. So this system of operation may include all aspects, including receiving of the material, inspection of the material, storage of the material, production, assembly, packaging, warehousing, shipping and transportation, all as a systemic approach. So everything needs to be integrated within the material handling plan. That is the principle, guiding principle of the Material Handling Institute. So then there is a unit load principle which handles the product in as large a unit load as practical, so that number of times the handling has to happen goes down, because now at a unit you can supply many materials together. Obviously there has to be a very important space utilization aspect. So space utilization principle makes effect utilization of all cubic spaces. Wherever possible for storage applications introduce vertical spaces. Wherever there is a question of fitment or assembly, you have to lay out the material horizontally. So moving from a vertical into horizontal has to be done on a a three-dimensional map has to be prepared, which can be of optimum distribution. Standardization principle again, which standardizes the material handling methods and equipments whenever possible. Obviously you are limited by the industry which produces these handling methods and equipments, and you cannot have a basic requirement in your material handling which needs a specialized equipment for that particular handling situation. So then there is ergonomic principle which recognizes human capabilities and limitations by designing easy material handling equipments and procedures. This would be more because you want to reduce the burden or the load on the individuals who are involved in the material handling, and they can effectively interact with the equipments, material handling equipments, and so therefore ergonomic planning of the material handling is very much needed. Then there are many other aspects like energy principle. Nowadays energy obviously is very precious, so you have to include the energy consumption of material handling systems and material handling procedures when making comparisons or preparing economic justifications. This comes actually at the level of selection. So therefore more of gravity feed vis-a-vis, let us say, things where active energy is needed, active material handling systems, they're being replaced slowly by the gravity fed systems because of the minimization of the energy principle. Obviously, the minimization of adverse effects on the environment is a big issue in selecting the material handling equipment, particularly and the procedures. You should not be too far away from the environmental norms whenever you are planning a material handling system. As far as possible, mechanize. So, mechanize the handling process where feasible to increase efficiency, economy in handling of materials, so on and so forth. You should have a flexibility principle where use methods and equipments that can perform a variety of tasks, so that you can reduce your capital expenditure on the material handling. So, you can design probably a roller chute that can be used for offloading from the truck a bin as well as a some kind of a specialized jig, for giving different components, so that it can be located near to that assembly point where it is to be delivered. So, this flexibility in choosing the equipments and the materials, which actually includes roller chutes and conveyors, or even vias and belts which are used for the various transportation mechanisms, there has to be overall flexibility governing the choice. So, by and large, we want to make systems which are simple and easy to use. So, simplify the handling, and that can be done by reducing or combining unnecessary movements of the equipment. So, that is what the simplification principle states. Not many crisscross points, particularly parallel flow of the material would be a much better alternative. You have gravity principle. So, utilize gravity to move material wherever possible while respecting limitations concerning safety, product damage and loss. You have safety principles. So, provide safe material handling equipments and methods that follow the existing safety codes and regulations in addition to the accrued experience. And then obviously, you have computerization principle, you have systems flow principle where you integrate data flow to physical material flow in handling and storage. Some of these are very important for lean manufacturing issues, so on and so forth. Layout principle where you prepare an orientational sequence and equipment layout for all viable system solution, and then select the alternative system that best integrates efficiency and effectiveness. So, some of these principles are more or less used by at the planning level when you are defining the overall material handling system. One of the aspects or one of the very important issues which come up particularly in automated factories when we are talking about automated material delivering at the place of the fabrication or assembly of these materials is the use of so called automated guided vehicles or AGVs. So, an automated guided vehicle really is a system, it is a vehicle system which is operated with battery power, and it is by and large driverless. So, you have to have a path and a programming associated with such a vehicle, so that you can have the capability of auto unloading and loading between different places, particularly on large assembly lines, etc. So, it belongs really to a class of highly flexible, intelligent and versatile material handling systems used to transport materials from various loading locations to various unloading locations throughout a facility. And particularly in the industrial automation, it is a very important component when we are talking about high volume production. And the whole idea here is that the path planning has to be done in a manner so that there is a sort of a less interaction while movement and more or less parallel flow of material movement along with the AGVs. And not only that, there should be a auto mechanism within the AGV which should be able to avoid collision. So, in a manner, although it is not a complete robotic system, you can say that it is at least a partial robotic system which would have some intelligent capabilities like sensors, etc. built in, and the directives can be given to it through a path which can be laid out either as a fluorescent light path or paint path, or as some kind of a electronic assistance by an underground cable, so that it can help to move the AGV in a particular direction from time to time. So, obviously, these automated guided vehicles are becoming a very important and inseparable part of flexible manufacturing system installations these days. So, what are the main components of an AGV? So, obviously, the first is the vehicle itself. It is used to move material within the system without human operators or human involvement. You have the guide path. So, it guides the vehicle to move along the path which is desirable for it to take. You have to have an onboard control So there is some kind of a controller which is there, controller unit, which monitors and directs system operations, including feedback on moves, inventory and vehicle status, so on and so forth. And there has to be some kind of a overall computer interface which can interact with this whole flexible manufacturing system, and it can automate the process of material delivery and loading and unloading wherever needed. So such systems are normally mainframe based systems, which is a sort of a host computer, and it plans the delivery of materials falling short at different places along a FMS system. There are several different types of AGVs which are available to meet the different service requirements. They include AGVs towing vehicles, AGVs unit load transporters, pallet trucks, forklift trucks, light load transporters and assembly line vehicles. So these all form under the category of the automated guided vehicle system. Let us look at the guidance systems in an AGVS. The primary objective of a guidance system in an AGVS is really to keep the vehicle in a pre-designed path or a track, so that the very less interference between two or more vehicles plying parallelly to different stations to meet their material requirements. The main advantage of the AGVS guidance is that the guide path that can be changed easily at low cost compared with the cost of modifying fixed path equipment such as conveyors, chains and tow lines. Moreover, the guide path is flexible, that is crossover of the path is possible and the path does not obstruct other traffic. So it is all by signal matching or frequency matching that some selection of the path can happen if you have a unit which can recommend a particular frequency or do a local frequency selection on the vehicle unit itself. So typically there are either wire guided systems or there are optical guided systems. I will probably give you a brief of both. So in the wire guided systems, an energized wire is embedded in the floor along the AGV guide path. The antenna of the AGV sensors and follows the embedded wire, and wherever there is a path selection issue, you can do it with either a path switch or you can do it with some kind of a frequency identifier. I am going to come into the detail of that just in the next step. The other broad category is the optical guidance, which comes from a colorless fluorescent paint, and there are particles which are painted, which are fluorescent in color or even taped on the carpeted, tiled or concrete floor. And there are photo sensors on the vehicle which will read and track these colorless particles and process the information signal. The system would permit a clean operating environment this way. You do not need to really get into the additional work of laying out wires wherever the new path needs to be developed within an assembly line, let us say. Otherwise also the systems present are very complex in nature. So typically the optical guidance system is used for most of the time when we are talking about the AGVS systems. There can also be inertial guidance systems. The system has an onboard microprocessor that is used to steer the vehicle on a pre-programmed path. A sonar system is used for obstacle detection and gyroscope for the direction change in this particular case. There can be an infrared. So typically in this category, a sonar sensor is used for performing the obstacle detection. An algorithm, control algorithm is used wherever there is a reflected wave coming out of an obstacle. I would just try to direct the vehicle into a different track. Okay. So therefore there are no obstacle collisions in the process of the movement of the vehicle. There is also a gyroscope which actually tries to sense the different aspects of motion related to the vehicle, on which one can calculate how much distance the vehicle has gone and how it needs to go, so on and so forth. There is also an infrared guidance system where the system consists of an infrared light transmitters, reflectors mounted on the roof of the facility where this AGVS system needs to be installed. So these reflectors reflect the light, and the radar like detectors relay the reflected light signals to the computer, which then determines the position and direction of travel of the vehicle. So you can program from a control station where the AGV is trying to go or it has to go, so on and so forth. There are laser guidance systems in a similar manner, and in this system a laser beam is used to scan wall mounted barcoded reflectors, gives you an idea of the positions they are accurately located earlier. You have a library of such reflectors all around in the facility, so you can actually maneuver based on the readouts of the barcodes and then try to direct the AGV to go toward a specific barcode when you are doing this. Then also there are teaching type guidance systems. In this system a neural network concept is used. A programmed vehicle is actually physically taken by walking through the desired route, and the computer learns about that, and then again programs whenever it is running on a programmed mode. After this teach mode is over, it can actually go through the similar kind of a route as has been planned earlier. It then informs the host computer what it has learned about, and the new path is used for control guidance of the AGV, so on and so forth. So these are the various types of guidance systems which are used in the AGVS. Let us look at how to steer or how to perform steering control, local steering control. So obviously steering control of an AGVS can control the vehicle to negotiate a turn and to maneuver physically in different ways. There are two principal types of steering controls that these AGVS has. One is called the differential speed steer system, and another is the steered wheel control. So let us look at both separately. So in the differential speed steer control, the system uses an amplitude detection type of guidance sensor, and the control is based on balancing of signals from the left and the right side of the sensor. Okay, so that is how, so basically the signals come because of the rotating wheels, wheelbase, from the wheelbase of the AGVS. So it is in the front of the vehicle typically, and so if you have the left and the right signals having a mismatch, obviously there has to be some kind of a steering action so that the AGV is put back into track. Okay, so obviously the differential speed would happen to set in a turn, but if you do not want to turn or you want to avoid the turn, you have to give a reverse signal so that it keeps back on track. That is the whole idea. So whenever a difference exists between the right and left signals, the steering compensates by correcting the steering. Vehicles with differential speed steer controls have less tracking tolerance than vehicles with steered wheel controls. The steered wheel control system uses a phase detection type of guidance sensor to determine whether the vehicle is to the left or right of the path by detecting the positive or negative phase of the sensor signal, and this signal is typically obtained from a guide wire path. So such steering controls actually can be utilized only when there is a particular signal path which is into picture, which is actually a wire path kind of a control. Obviously if you have an optical signal in place and you have a fluorescent readout, if there is a change in the color coding of the fluorescence, only then this kind of a frequency based selection can be obtained for doing steering control on the AGVS. Let us look at some of the routing systems. So there are two different methods which are used for it. One is called the frequency select method and another is a path switch method. Let us look into both aspects. So this right here is a routing scheme of the AGVS. It is a simple guide path layout which is given here, and this is the frequency select method being incorporated on the guide path layout. So obviously the AGVS has to perform a decision making whenever there is a question of a turn that it needs to be executing. So if there is an AGVS vehicle moving all the way to this junction, at this junction it has to take a decision whether it would try to take left or would go forward in this particular direction. So how do we do that? So consider this simple layout given in A and the frequency select method demonstrated in B. The location where a path splits into two or more than two separate directions is called the decision point, like right about here is a decision point, or maybe here you have another decision point, or probably here another decision point, wherever there is a splitting up into two or more tracks. So at the decision point the vehicle reads a marker which is a passive code device in form of a buried magnet, metal plate or other code devices. So in the floor where multiple frequencies are present to allow the vehicle to go into multiple directions. So the vehicle selects a frequency for the direction it wants to follow. So if supposing I had a different frequency on this end and different frequency here, let us say this is F1 and F2 which are stored on the floor through some kind of a metal plate or some kind of a barcode, you know. So the scanner at this particular position would try to select between this path, whether the path is going to be here or the path is going to be here, by looking at the differential frequencies here and matching with its database in the programmed path what frequency it needs to select for going into the correct path. So that is how you do the frequency select or frequency based select method. The other is a path switch select method. So in the system, the guide path is divided into segments that are switched on and off by separate floor controls. You can see here there is a control for this path, part of the path, and there is another control for this part of the path, and there is some kind of a control switch box which would then be able to cater by switching on different segments of this path. So only one frequency is used in this particular case, so you need not actually get a barcode or some other scanning additional installation in place. So at the decision point, the controls are switched on and off depending on the path to be followed, so that the correct tracking of the AGVS can happen at the decision point. So these are the two principal methods of doing the routing, the AGVS routing. Let us also look at some of the types of AGVs. As I had discussed before, you can see schematically how they look like. This is the towing unit, this is the unit load movement unit. You in fact actually see the unit heavy directional unit load movement here in the AGVS scheme. This is a real AGV in an industry which is carrying a unit load. Okay. So there is a fork truck unit, again there is a light load, and there is an assembly line unit. These are all different types of units. So the critical issues in the management of AGVS happens to be the guidance systems, the routing, the control systems of the AGV, and then obviously the main purpose, which is the load transfer. What is the capacity of the AGVS to take loads, and then how you can interface with other subsystems like the flexible management system, etc., so that you can actually get the requirement from the subsystem and then put into place so that the material handling happens in the place where it is needed in the right quantity, in the right time, so on and so forth, under the principles of whatever lean manufacturing issues industry has to go through. As regards the control systems, the AGVS have different kinds of control systems. Obviously there is a completely computer controlled system, there is also a remote dispatched control system, and then obviously the manual control system. So computer controlled systems happen to have all transactions and vehicle movements as controlled by a system controller, a main system controller, and basically the idea is that this process controller is going to be giving signals to the guide path, which is this unit right here, and then it also is able to display whatever is going on, and the computation basically as a requirement comes from the host computer. So the planning happens here based on the requirement received from the computer about the various requirements at different stations of the materials. So there is an input terminal, there is a host computer which would do all the computation regarding what material in what quantity at what place, and then obviously the controller would define the flow path in a manner so that the AGV can go to the correct location, so on and so forth. So mostly AGVS systems are more or less in a very high volume production computer controlled. The other mode is a remote dispatch control system. So in this system a human operator is required to issue instructions to the vehicle through a remote controlled station. So this is something which is more semi-human, you can say, but used in situations where the load on the AGVS system for doing material handling is substantially lower. Computer control would be needed when you are planning to have a bulk handling of the materials through the AGVS route. So basically the control system sends the destination instructions directly to the vehicle. So you basically as a human operator plan where the AGV needs to take what kind of load and deliver to what station, and although the human does not have any direct control over the AGVS vehicle, but it can actually plan and say that how much is needed at what station. So that is a remote dispatched control system, and the other one obviously is manually fully controlled. So the operator loads the vehicle and enters a destination into the onboard control panel of the vehicle. Vehicle is routed by itself to the designated destination through the guide path. So it also has to look into the other vehicles and the other traffic which is around for planning its own motion, try to take the shortest path that way. So there is some kind of an algorithmic planning which is involved to do the correct guidance using as less as obstacles on its path with the shortest route. But then again, this is a completely manually controlled, because the loading unloading has to be done at the operator end. So after reaching the final destination, the vehicle stops and waits for the operator to perform a direct unloading. So here the AGVS has to be dispatched back by the concerned assembly line operator or the operator who is waiting for this particular material. So as soon as the material goes to the station, he has to dispatch the AGVS back by sending a signal or a switch, so that the AGVS can start moving back. So by and large, these manually controlled systems are quite simple and least expensive of all the control systems. Some of the industries do employ these kind of systems, particularly in bumper paint shops or other paint applications, where there are particular requirements based on the different vehicles which are in place, and also sometimes between bumper paint shops to the assembly line where the bumper is fitted, there would be a requirement of quite a number of these manually controlled AGVs. Otherwise, in most of the applications where there is a high volume of goods to be planned and delivered, a preference is always for the computer operated or the fully computerized computer controlled AGV systems. So having said that, there is obviously going to be an interface of the automated guided vehicle system with the other systems, subsystems which are available. These include automated storage retrieval systems, the ASRS, flexible manufacturing systems. Sometimes there are CNC machines, so they need an interface with these machines. They also need an interface with process control equipment and various other shop floor control systems which are available. So this interface may be a thorough, this maybe either through a distributed data processing network, or through a unified host computer which will actually do all the steering and maneuvering based on data from all these different subsystems, but the integration becomes a real challenge at a host computer level. Would also like to learn a little bit about the number of automated guided vehicles which are needed, particularly in a situation to balance the load of deliverance of materials. So let's say let's sort of calculate the minimum number of automated guided vehicles which would be needed if the total average loaded travel distance of the vehicle is given as DD and the total average empty travel distance is given as DC, and the number of deliveries required per hour is given as NDR based on the demand, and the loading unloading time is given as TH, and also the traffic factor that accounts for blocking of vehicles and waiting of vehicles in line at intersections, etc., is given as TF. So if there is no congestion, the traffic factor can be considered to be 1. However, if when more than 1 vehicles are involved, the traffic factor would certainly be less than 1. Normally TF would lie between 0.85 to 1. Okay, that's how you have to plan your system as, or design your system as. So then and if supposing we consider V to be the vehicle speed, so then the total delivery time per delivery per vehicle, TDV, will be given by the sum of loaded travel time and loading and unloading time and the empty travel time as follows. So you have the total time for average loaded travel distance DD to be moved is DD by V, V being the vehicle speed. The total hold time where the loading unloading process happens is TH, and then obviously the total empty travel distance is DC, and that divided by V gives the total empty traveling time. So if we suppose that the number of deliveries per vehicle per hour is ND, so if we really wanted to look at the number of deliveries per vehicle per hour, it's sort of frequency of the frequency of trips, you can say. And so if supposing TDV is the total time of delivery of a single vehicle, the first aspect that we want to look at is that how the TDV will change if the traffic factor, which is basically blocking of vehicles and waiting of vehicles, is involved, would change. So the TDV obviously will increase because of the intersection or waiting. So therefore you have to divide this real, you have to sort of calculate this time real that it takes in case there is a traffic blockage or obstruction by dividing the TDF with the TF factor. So if the TF is low, supposing there is a low TF value. So obviously the total time needed for the delivery to happen, the real time of the delivery you can say would actually be higher than the total time of delivery that is needed only by looking into the loaded distance, unloaded distance and the loading unloading time summation. So if this were in minutes, so if the number of deliveries per vehicle per hour needs to be computed, it would really be the inverse of this real time. So it's a sort of frequency which can put into place, which we call ND here, which is actually 60 TF by TDV. So basically it is just the inverse of the real time that it would take for doing one delivery. So that's the delivery frequency for one vehicle. And obviously if we had NDR as the number of deliveries required per hour, so this NDR multiplied by the frequency or divided by this frequency, so or maybe just multiplied with the time of the real time of one delivery, which is actually the TDV by 60 TF, which actually give you the number of automated guided vehicles which are needed. Okay. So this is the deliveries per hour, and this is the total time needed for performing one delivery. So one delivery of one vehicle. So this is basically how you calculate the number of or total number of automated guided vehicles which are needed. Let us look at a problem example where Johnson & Johnson is planning to integrate the AGVS and obviously also the automated storage retrieval system, which I will just mention about after this topic, with their FMS system, and JJ is interested in estimating the number of AGVs required to satisfy the need of the manufacturing system. That means the system must be capable of making 51 deliveries per hour. So that is how they are planning, and they have already decided to install a laser guided path system, and unit load AGVS adequately serves the company needs. The following data has been collected. So the vehicle speed data is 180 feet per minute, and the average loaded travel distance per delivery is 540 feet, and the empty travel distance per delivery is 360 feet. We need to, and also the pickup and drop off time have been given to be half a minute each, and the traffic factor is 0.85. So we want to calculate what is the number of vehicles which are needed. So let's first look at the total delivery time. So total time per delivery per vehicle, TDV, is given by the total average loaded time, the total hold time plus the total empty loaded time. In this particular case, the average loaded travel distance is 540 feet at the rate of 180 feet per minute, so many minutes, plus the hold time and pickup time, that is the drop off pickoff time, is about close to 1 minute here, 0.5 plus 0.5, plus the empty travel distance is about 360 at the rate of 180 feet per minute, is about 2 minutes. So you have about 3 plus 1 plus 2 is about close to 6 minutes as the total delivery or total time per delivery per vehicle, and add on the traffic factor to this thing. I mean, the total amount of number of deliveries per vehicle per hour comes out to be 60 TF by TDV, which is 60 times of the traffic factor 0.85 by TDV, which is 6 in this particular case. So it becomes 8.5 number of delivery. So this is the delivery frequency per vehicle per hour, and obviously we need 51 deliveries per hour. So if this were the number of delivery for one vehicle in 1 hour, for a set of 51 deliveries needed, typically 51 by 8.5, about 6 vehicles would be needed to do this job of giving 51 deliveries per hour. Okay, so that's how you calculate the number of AGV vehicles which are needed, number of AGV vehicles needed. So, this is a sort of an optimum plan, and there are many other optimization issues like distance criteria, etc., which can come into picture when you have a realistic situation in place. So, I think I am kind of done with the topic of automated material handling control. The only other issue which is being left over is the automated storage and retrieval systems, and basically this is a most modern concept, particularly when you are talking about storing of high volume inventory material of lower sizes. So, the automated manufacturing systems such as FMS's flexible manufacturing system can provide quick changeovers to different part types and their cost effective production only if we can get the right parts, pellets, fixtures, tools, etc., to the right place at the right time. So, for this purpose their efficient system of storage and retrieval is needed, and by and large if it can be automated it is even better. So, that is why these ASRS systems come into place. So, basically what are the functions of the storage systems and some of the definitions of the ASRS. So, receiving, identification and sorting, dispatching to storage, placing in storage, storage, retrieving from storage, order accumulation, packing, shipping and record keeping for raw materials, purchase parts, work in process, finished products, pallets, fixtures, tools, spare parts, rework and scrap, office supplies and so forth have traditionally been considered to be the function of all these storage systems. And for a particularly an automated storage retrieval system, it typically comprises of the following. One is a series of storage aisles having storage racks, and then also storage and retrieval machines, normally one machine per aisle to store and retrieve the material. One or more pickup and delivery stations where materials are delivered for entry to the system and materials are picked up from the station. This for example shows such a delivery point. So, you have several bins as you can locate in this particular regions as kept as rows and columns, and they are all numbered, and similarly there are different rows and columns on the other side. This itself is the machine which would actually go and retrieve a particular bin from a particular part and bring it as programmed. So, this is how a real ASRS system would look. So, typically when you are talking about high level inventory of tools for an assembly line for example, or let us say pellets and fixtures for a press shop or a die shop or even like a weld shop, so on. So, you have to use some of these ASRS systems in place, particularly when the volume of productions are very high volume. So, typically the whole ASRS system, as can be seen in the width of this whole ASRS system, is defined as various zones, and there is a certain terminology used for these zones. For example, we have storage space, which actually reflects one such container here, which is basically meant for storing a certain amount, certain part by a certain amount. It is a 3-dimensional space in the storage rack that is normally required to store single load unit of material. There is also a bay. So, the bay is somewhere in between here, vertical stack of storage locations from the floor to the ceiling, okay. And obviously there is a row, a series of bays placed side by side. So, you can have different rows for one series of bays as can be looked into here, and then another row, these are all horizontally placed series of bays as rows. We have an aisle unit, which is the space between the two rows for the ASRS machine operation. So, typically this is the stacker machine that is in picture as you saw earlier, and there is a stacker machine at each of these locations, or sometimes even a single stacker which can go and access some of these rows and columns where a particular unit needs to be carried from, which is otherwise stored in that particular space. So, you have an aisle unit, which is the aisle space and racks adjacent to the aisle, this particular unit through which the stacker machine can move. And then you have storage racks, a structural entity comprising storage locations, bays and rows you can see these are the different storage racks which are into picture. Okay, so this is one rack, then this is again a second rack, a storage rack, okay, this third storage rack, fourth, fifth, so on and so forth. And obviously there is a storage structure. A storage structure comprises of storage racks and is used to store inventory items. Usually it is a steel frame structure that is designed to handle the expected size and weight of the stored items. So the infrastructure which is needed to house these bins, these different bins, is basically the storage rack, storage structure. And then obviously you have the storage retrieval machines, the SR machines, move items in and out of the inventory. The SR machine must be capable of vertical as well as horizontal movements, must be able to place and remove the items from storage as well as interfacing the entry exit points to the ASRS. So that is how you define the ASRS mechanisms. So obviously the terminologies which are used here is basically, one is the storage modules. So the storage modules are used to hold the inventory items. The modules may be pallets, bins, wire baskets, pans and other containers. Typically the principle of design here is to make it as visible as possible, so that the basket can be seen at a glance and it can be planned as to what is falling short, so that it can be replaced. The storage modules must be designed so that they are of standard size, capable of being stored in the structure and moved by the SR machines. So these pallets are very to the dimension. And then there are pickup and deposit stations, so which allow the inventory into the system. It is necessary to have pickup and deposit stations. These are generally located at the end of the aisle, so that they can be accessed by the SR machines from the external material handling system. So this all combined together formulates the ASRS system, as you can see here. There are a lot of additional considerations which go into the design of ASRS systems, which are probably not going to cover in this particular course, but typically a highly automated industrial system would typically have robots at one end, and then there is also a automated material handling system like the AGVS that we discussed in details, and also this automated storage and retrieval systems. These are over and above the conventional chutes or conveyors or rollers or gantry kind of systems which are already in place in most of the industries. So this brings to a completion this particular module of the course on manufacturing systems technology part 2. And typically in this module we in this particular course we covered over and above some of the things which were left over in part 1, like quality and how you can define quality and how you can measure quality by statistical quality control principles. And we also tried to cover some of these automated material handling systems, etc., that the modern day industry envisions to have. Thank you very much for attending this course, and I wish you all the best for your examinations. Thank you.